Hello everyone. In lecture 5, let us talk about the discrete convolution. In this example, we have to compute the convolution yn of the digital signals given by. So x1n is one sequence which is given by 1 minus to 1. x2n is other sequence. It is 1 from for n 0 to 5 and 0 otherwise. So in time in continuous domain, if the convolution of these two sequences, let us say, will give us yn. So this is the convolution sign. But if we take the z transform, we know that the convolution in analog domain will in the discrete domain it will become the multiplication of the two sequences. That means if we take the z transform of x1n, so it gives me 1 minus 2 z to the power minus n plus z to the power minus 2. x2z will be given by, because it is 1 from 0 to 5, 0 otherwise 1 plus z to the power minus 1, z to the power minus 2 up to z to the power minus 5. Now if we multiply these two, here in the z domain we have to multiply the two expressions, and then we will get the final yz, which is actually the convolution of, which is actually the multiplication of x1z and x2z, but it is equivalent to the convolution of x1n with x2n. Now here if you see this expression we get, you take out the coefficients of these powers of z. That means for z0 we will get this one, z to the power minus 1, this is minus 1 here, z to the power minus 2, minus 3, minus 4 are zeros, z to the power minus 6 is minus 1, and z to the power minus 7 is our next final output sequence. So this is the convolution result of this sequence x1n and x2n. All right. Now let us look at this system. We have to determine the system function hz for this structure given. This is xn, which is the input, yn is the output. It is delayed by 1 unit of time and then multiplied by a. That means we get this yn will be delayed by 1 unit of time, will give me yn minus 1. When multiplied by a, will give me a yn minus 1. It is then added with xn, and which makes the final output. So yn is equal to xn plus a yn minus 1. This becomes the difference equation for this system. If you take the z transform of this difference equation, you will get yz for yn xz plus a, because here yn minus 1 is there, so therefore you will get z to the power minus 1 yz, and a here in the difference equation it is being multiplied by a, so exactly the same scaling factor will come, which is a. Now if you, from this equation, if you get a yz by xz, which is our transfer function hz, this will be equal to 1 over 1 minus a z to the power minus 1. All right, this is how you can get the system functions or the transfer functions of various systems. Now these are some basic z transforms. For example, delta n is 1, un is 1 over 1 minus z to the power minus 1, alpha n un is 1 over 1 minus alpha z to the power minus 1. We can straightway apply these z transforms of these basic signals in our numerical problems. Now this is signal and this is equivalent transform. Xn is xz. This is a of xn plus b. Yn will be a of xz plus b yz. So x of n minus k, when the x is delayed by k units of time, so it will be z to the power minus k xz. A and xn will be x z by a, x of z by a. X of minus n is x of z to the power minus 1. Xn convolution yn will be equal to xz into yz, and xn will be minus z dz dy dz of xz. All right. So these are some standard z transform properties. Now we know that we can recover this discrete sequence back if we take the inverse z transform of the xz. So we will get the xn sequence back. Now let us take one example in which x is equal to z to the power minus 1 divided by 1 minus 0.25 z to the power minus 1 minus 0.375 z to the power minus 2. So what we do is we multiply the numerator and denominator by z square, right? So this will z to the power minus 1 will become z. We do this to get rid of z to the power minus powers, right? Z by z square minus 0.25 minus 0.375. This is a quadratic equation, or this we can call this as the characteristic equation. If we take the roots of this equation, roots will be 0.75 and minus 0.5. So we can factorize this equation. So it will become z over z minus 0.75 into z plus 0.5. Now we can apply the partial fractions here. So the partial fraction, once the partial fractions are applied, we can get the values of these two constants. So after getting these two constants, we can put a this expression in this form, which clearly gives me the discrete sequence back from this expression. Let's say this is 0.75 to the power n minus 4 by 5 is taken common, and this will be equivalent to minus zero point 0.5 to the power n. Actually, this property of the Z transform is used here. Alpha n un is 1 over 1 minus alpha Z to the power minus 1, and we can recover the sequence back. Now let us try to understand the relationship between the Z transform and the Laplace transform. Actually there are two variables. One is Z and other is S. Z is a complex variable which belongs to the digital domain or discrete domain. S is a complex variable which actually belongs to the continuous domain or analog domain. So we can put Z equal to e to the power S capital T, where capital T is the sampling period. Now S is actually equal to sigma plus j capital omega. We replace S here with this value. Now we can separate out the exponents e to the power sigma t dot e to the power j capital omega t. We know that capital omega t is actually given by small omega, which is the digital frequency, and digital frequency lies between minus pi to pi. This is the fundamental period of the digital frequency. So if we take the magnitude of z will be equal to e to the power sigma capital T, and its angle will be given by this omega. Now omega is equal to capital omega t, and we know that capital omega is 2 pi f. Capital T we can put it as 1 over fs. So this becomes our digital frequency. Now, as omega varies from minus infinity to infinity, the S plane is mapped to the Z plane as shown in the figure. This figure, if you see, this is the S plane. This minus j omega axis is mapped inside the unit circle, right? If we put the left hand S plane is mapped to the inside of the unit circle, and the right hand side S plane maps to the outside of the unit circle. If we just take this imaginary axis and try to join the ends of the extremities, then you will see that the left hand side of the S plane will be, left hand side of this imaginary axis will go inside the unit circle, and right side will go outside the unit circle. Now, if we put sigma equal to 0, so that will give me, if we put here sigma equal to 0, so that means mod z will be equal to 1. That means this defines the unit circle, the perimeter of this unit circle, right? And in this case, if this becomes the unit circle, then omega, small omega will vary from 0 and it goes to pi, and from minus, if we take the other direction, it will go from 0, minus pi by 2, and minus pi. Now if you put, as I was saying, if you put sigma equal to 0, in that case this magnitude part will become 1 and z will be equal to e to the power j omega. This will actually give the frequency points, this will actually map the frequency points in the S plane to the Z plane. This is how the frequency points in the S plane are related to the points in the Z plane unit circle. All right. Now, frequency response estimation, there are many instances when it is necessary to evaluate the frequency response of discrete time systems. So, frequency response of a system can be readily obtained from its Z transform. What we have to actually do to obtain the frequency response of a system is that in Hz, for every Z you put it equal to e to the power j omega, and you get the frequency response of the system, where omega will of course vary from minus pi to pi. So this is actually taking the Fourier transform of the discrete time system. Now let us take an example. Hz is equal to 1 over 1 minus a z to the power minus 1, where a varies from 0 to 1, right? And let us say a is equal to 0.6. We have to find h omega. Now h omega will be found out by putting z equal to e to the power j omega. All right, let's see how. If we put e to the power j omega, so this will be 1 over 1 minus a e to the power minus j omega. We use the Euler's identity here, which is e to the power j theta is equal to cos theta plus j sin theta. So we get this expression. This is the frequency, h omega is the frequency response of the system, whereas mod h omega is the magnitude response. Once we take the mod, so this will be the magnitude will be the squares, and then take the under root, and you will use here the identity cos square omega plus sin square omega is equal to 1. So the expression will reduce to this equation. Now if you see this graph, along the x-axis is small omega, which is the digital frequency. Along the y-axis is magnitude response. Now for omega equal to 0, if you put omega equal to 0 here, it will be 1 minus a whole square under root. So square will cancel with under root. So the value left is 1 over 1 minus a. When you put omega equal to pi or minus pi, it will be equal to 1 plus a whole square under root. In that case, this value will be 1 over 1 plus a. Right, the rest of the things we all know, because minus pi will belong to f minus fs by 2 in the analog domain, and pi will belong to fs by 2 in the analog continuous domain. Now let us try to understand the pole zero description of the discrete time system. The zeros of Z transform hz are the values of z for which hz will be equal to 0. If hz is expressed in this form, which is yz by xz, right? There are two polynomials, one is yz, the other is xz. So this is the numerator polynomial, this is the denominator polynomial, and this one is important here, that will make it as a rational function. Now if we factorize the numerator polynomial and the denominator polynomial, you will get a general expression like this. Now if you see z1, z2 and zm values, these are those values. If you put these values here in this expression, this will make hz to go to 0. And if you put P1, P2 and PL values, these values will make the HZ expression go to infinity. So poles, zeros take the value of HZ to 0, poles take the value of HZ to infinity, right? Where A naught is a constant, which is the gain of the system. Now the complex quantities Z1, Z2, Z3 are called zeros, and the complex quantities P1, P2, P3 are called the poles. We thus see that hz is completely determined except for the constant a. We will not be able to determine the constant a naught by the values of poles and zeros. This is only the system gain, the DC value of the system. The information contained, DC gain of the system, the information contained in the Z transform can be conveniently displayed as a pole zero diagram in the figure as shown in this slide. There in this figure, if you look carefully, there are three poles. One pole is here, the other pole is here, and these two poles are complex conjugate pair of poles, right? And this is a real pole which lies on the real axis. Now this is a z plane. The x-axis of the z plane is the real part of z, because z is a complex number. The y-axis is the imaginary part of z, and mod z is equal to 1. So this is the circle. And here is a 0 also, which lies at z equal to minus 1. All right. In the diagram, this cross will represent the poles, and this 0 symbol will represent the zeros of the system. The poles are located at 0.5 plus minus 0.5 j. So these are the complex conjugate pair of poles, and one pole is there as z is equal to 0.75, a single zero is at z equal to -1. Two other zeros are also there in this system because the number of poles and zeros will remain the same. Those zeros are at the origin. Now, so any zero or pole at the origin do not contribute to the transfer function of the system. An important feature of the pole zero diagram is the unit circle. The pole zero diagram provides an insight into the properties of a given discrete time system, that whether how the system will behave, whether it's a low pass, how the characteristics of the system will look like. From the locations of the poles and zeros, we can infer the frequency response of the system as well as its degree of stability. Now, for a stable system, all the poles must lie inside the unit circle. This is a condition. All the poles must lie inside the unit circle. So, zeros may lie inside on the circle or outside the unit circle. Even the poles cannot lie on the unit circle because the system will then become oscillatory at that point. So, zeros can lie inside on the circle or outside the unit circle. Now let us determine the transfer function hz of a discrete time system with the pole zero diagram shown here. Now this is the pole zero diagram shown. So let us look at the poles. There are two poles which are the complex conjugate pair of poles, and two zeros are there which are also the complex conjugate of pair of poles, pair of zeros. So this zero is plus j plus 1j. This zero is minus 1j. So K is a constant factor which is the gain of the system. So we cannot determine this from the pole zero diagram. So let us put a constant here K. So two zeros are there, plus J1 will represent Z minus J1 and minus J1 will represent Z plus J1. Two poles are the complex conjugate pair of poles. So we will say Z minus the first pole, Z minus the second pole. So we will get this expression. If you solve it further, you will finally get this expression for the transfer function of the system, which is actually represented by this pole zero diagram. Now we have to determine the pole zero plot in this case. Now pole zero plots are plotted in the discrete domain as the x-axis will have the real part of z and the y-axis will have the imaginary part of z. Now if you look at this system, hz is equal to z divided by z minus a, that means it has got one zero and one pole. The zero is at origin and the pole is at z is equal to a. So this is the pole and this is the zero. This is the pole zero plot for this system defined by this transfer function. Now let us determine the pole zero plot for this system. This system says that hz is equal to z to the power m minus a to the power m, z to the power in the denominator it is z to the power capital M minus 1 and z minus a. So if you factorize the numerator, you will have this kind of equation z minus 1 and so on up to z of minus m, and in the denominator you will see that z to the power capital M minus 1, because this z to the power minus a will cancel with 0 at z is equal to a. The 0 z is equal to a cancels the pole at z is equal to a. So if we take an example with capital M equal to 8, if you put capital M equal to 8, so this will be z to the power 8 minus a to the power 8 divided by z to the power 7 z minus 8. So that means 7, that means uh, this pole z, the pole at z is equal to a will be cancelled out by 0 in the numerator, right? So thus this so how many poles are there at z is equal to 0? uh, so there will be how many poles? 1 2 3 4 5 6 7. So total 8 zeros are there and 8 poles will be there. So one pole is cancelled out here, right? And there will be 8 poles which will lie on the origin, right? So these 8 poles will lie on the origin because m is equal to 8. So this is how determine the pole, because it is z to the power m minus 1. Uh, so that means m is capital M is equal to 8. 8 zeros are there which lie on the unit circle. So one pole is there at the z is equal to a. Actually, here will be 7 poles, right? 7 poles will exist at the origin, and one pole gets cancelled with 1 0. This is 7 here, not 8 poles. Total number of poles in the system are 8, but 7 poles will be at the origin, and one pole at z is equal to a will be cancelled out with 1 0 at z is equal to a. Now consider a system with at Z with two complex conjugate poles in the. So we have two complex conjugate pair of poles. The first pole is represented in the polar form as P1 is equal to R e to the power j omega. The second pole P2 is R e to the power minus j omega. So these are the two poles, and a 0 is there at origin. So Z1 is equal to 0. So we have to determine the we have to try to determine the transfer function of this filter. So a typical transfer function will be represented by z is, which is 0 on the numerator, and these two poles z minus r e to the power j omega and z minus r e to the power minus j omega. So two poles will be represented by this. Now you you perform the partial fractions. So after performing the partial fractions by taking a and b constants, you will get this expression. From this expression, if you try to solve it further, all right, then this if you take out um, 2, because if you take out z from this part, this will become 1 minus r e to the power j omega z to the power minus 1. Same will happen here. So you will get here 1 over this. If you take z common from here also and here also, this that z will be cancelled out with this z. So you will be left with this expression if you perform little bit of manipulation. Then you can recover the discrete sequence back, because this is 1 over 1 minus alpha z to the power minus 1. So we can say that this is the expression of hn, and if you solve it further, this is the impulse response of the second order system with complex poles, where omega, small omega, is the frequency of oscillation. We will talk about this complex conjugate pair of poles in more detail in the resonant filters, and we will see that how the resonance takes place and how you can design band pass filters from here. We note that the impulse response will decay away to 0 provided R is less than 1. If you look at the now, if two complex conjugate pair of poles are there, now if R is less than 1, so this response, because you get the sinusoidal response because there is a sine function here. Because of this sine function, the function will look like a sinusoidal waveform, and it will decay, exponential decay sine wave when R is less than 1. So it is a stable system. But if R is greater than 1, that means the poles are outside the unit circle. In that case, the system it will not converge, rather it will diverge, so exponentially increasing when R is greater than poles outside the unit circle. So here, poles on the unit circle, so you will get a sinusoidal waveform, right? But one real pole inside the unit circle means you will get a monotonic response, and that monotonic response is of a kind of low pass filter here. Now if the poles lie on the unit circle, what will happen? It will not decay, rather the system will oscillate with certain frequency omega, and that will be known as the frequency of oscillation. So it will not decay. In that case, the system will remain unstable. Now, a system that is both stable and causal must have all its poles inside the unit circle. We cannot have a pole outside the unit circle, since the inverse transform of a pole located outside the unit circle will contribute either a right-sided increasing exponential term, which is not stable, or a left-sided decaying exponential term that is not causal. So in both cases, the system will become unstable. Now let us try to sketch the magnitude response for the system having the transfer function. Now this is the transfer function given, right? The hz is equal to 1 plus z to the power minus 1 divided by, so if you see here, this the system has a 0 at z equal to minus 1, and it has two poles at z equal to uh, my, 0.9 e to the power minus j pi by 4. All right. So these two poles are the complex conjugate pair of poles, right? Two poles are there, so these poles exist at this is actually plus minus j pi by 4, because this pole is e to the power j pi by 4, and this pole is e to the power minus j pi by 4, so it will be plus minus j pi by 4. So magnitude response, if you see here, 0, now let us have the pole 0 diagram. So these two poles are there, one, this is one pole, this is the second pole, and they are placed at an angle of pi by 4, because this is the frequency of the omega is given by pi by 4. So this omega is pi by 4, so one pole is located zero point 0.9 distance away from the origin, which is also given 0 0.9. So angle is also given, um, and the magnitude is also given, that how far the pole is located from the origin. So this pole is here, the other pole is here. Omega equal to 0 starts from here, right? And since the poles are inside the unit circle, so therefore it is a stable system, and 1 0 lies at z equal to minus 1. So 1 0 lies here at z equal to minus. So if the 0 lies here, that means omega is equal to pi. So at pi at z, which is the magnitude response, will go to 0, right? So this 0 tells us that the magnitude response will go to 0 corresponding to omega equal to pi. Now these two poles are located at pi by 4 angle, right? Because they are complex conjugate pair of poles. In that case, there will be resonance at pi by 4. Once the resonance will take place, there will be a peak at pi by 4, right? We will talk about the resonance and the complex conjugate pair of poles more in the coming lectures, but at pi by 4 there will be a peak. So it is very evident from this transfer function. What we are actually doing is that from the transfer function we have to actually make the estimate of the magnitude response, not the exact magnitude response, but we are trying to see from the pole 0 diagram that what should the magnitude response look like, right? We know that these two poles are there, zero point 0.9 away from the origin, at an angle of pi by 4. Two complex conjugate pair of poles are there, so there will be a peak at pi by 4. This is 0 at z equal to sorry, omega equal to pi, so it is 0 here. So the approximate response we can predict will look like this. We need not to go to the left side of this graph, because whatever is there on the right side will be a replica on the left side, because the magnitude response is an even function. So these two will be related to each other through even function property. All right. So that means once this transfer function is given, we can directly try to plot the frequency response, or we can at least estimate the frequency response, that how the frequency response will look like. Okay. Now, let us try to solve this question. This question says that sketch the approximate magnitude response from this pole 0 map. Now, we have two complex conjugate pair of poles at omega equal to pi by 2, right? and two zeros at omega equal to minus pi and pi. So that means that's very sure at minus pi and pi the magnitude response will be 0. At pi by 2 and minus pi by 2 it will peak. So you will get an approximate response like this. Very clear from the pole zero diagram. Now let us try to look at this question in which two zeros are there corresponding to omega equal to pi by 2 and two complex conjugate pair of poles are there at omega is equal to pi by 2. So what will happen, that is very sure, at pi by 2 and minus pi by 2 the response will go to 0. Now because these poles are there, the complex conjugate pair of poles are there and zeros are also there, so there it will ultimately lead to the broadening of this pulse shape. This will broaden out and it will behave like this. Since zeros are also there at pi by 2 and pole is also a complex conjugate pair of poles are also there at pi by 2, the response will come to 0, but ultimately the overall response will broaden out. The pulse will broaden out here because of the existence of the poles and zeros at omega small omega equal to pi by 2.